Okay, today we're going to be talking about our project, which was essentially to perform classification on different types of cancer in patients. So the aim of this project is essentially to show that there is a link between miRNA and the detection of cancer. So miRNA are small molecules in the body which can supposedly be used as biomarkers for showing cancer progression in patient. This is especially helpful because currently the only tried and tested methods of finding cancer progression is through invasive surgeries. And so if these biomarkers can be shown to be useful indicators for cancer, then patients can be saved a lot of time and trauma. And also it's possible to detect cancer at an early stage. So there are really important applications to this data that we have. So now we're going to talk a little bit about our data set. This data comes from 21 different problems, which essentially represent different types of cancer. There are almost over 970 features, which all are different miRNA signatures. Problem ID is another feature we have in our data set, which just corresponds to the type of cancer that observation belongs to. Our target variable has a lot of imbalance, but it's interesting in that every single problem ID, the response variables corresponding to that represent different things. So for instance, a 0 for problem 1 can represent something different for a 0 for problem 11. So what I decided to do is create this target variable distribution heat map, which gives a sense of how imbalanced the classes are for each individual problem ID. Now, it may be a bit confusing here, but it's important to remember, like I said, that the column 0 is different for every single row. So on the top here, for instance, problem 1, it's has a heavy class imbalance with a lot of values of 0 in the target, with not as many 1s in the target. And then for problem 5, almost every single observation falls into the category of 0. But remember that that 0 is different from the 0 for problem ID 1. Finally, all 978 of the individual miRNA values are continuous numeric features. So that allowed us to do create models a bit easier. Now, for some attempted methods, we're going to move on to our successful methods next, but I'd like to talk about some things that we attempted. So since there are so many different miRNA signatures, we wanted to find some way to reduce that feature space. So we used PCA to reduce the dimensions. We also tried to do some oversampling using ADASYN and SMOTE techniques. However, neither of these techniques improved our validation performance after using cross-validation, so we decided to ditch those for a simpler model. We also attempted some other models such as random forest and logistic regression, but in the end, our successful models, which will be shown, were the ones that were selected.
So yeah, like Zach was saying, we ended up choosing the XGBoost model, which ended up giving us the best results overall compared to logistic regression and random forests. So our first model was an XGBoost model trained on the entire data set. And we performed a randomized search CV and came up with the parameters shown here, 50 estimators, a max depth of 3, and a learning rate of 0.3. And we had a marginally okay prediction and log loss in the validation set. And we ended up getting a pretty decent score on 40% of the test data. And for our second model, we ended up training 21 different XGBoost classifiers. And the way we did that was we ended up putting it in a for loop and separating out by each problem ID. So each problem ID or each type of cancer was trained separately. And we ended up doing the same randomized search CV to get the hyperparameters for each of those models. As you can see on the right, some models were great, some models were not so great. We had a low of 38% in our accuracy, and surprisingly, we had 2 problem IDs that were 100% accurate from our model. So our prediction accuracy, as you can see, was much higher on this model compared to the first model. And it ended up going way down when we put it on the test set, which seemed surprising. And so our results at the end of the competition, we dropped 7 points compared to the rest of our classmates. Our public leaderboard scores were decent with the 2 models we chose. We had roughly 73.5% in our accuracy. And then once the remaining 60% of the test data was added in, our accuracy dropped down to 69.71. So in conclusion, we determined that the microRNA serve as valuable biomarkers for some of the cancer types, but not all, as we saw some abysmal accuracy scores when we trained 21 different models. We learned that there's a lot of flexibility and freedom that comes with creating models. And working with a complex data set is challenging, and models will benefit a lot from EDA and feature importance. And knowing the math behind all these different hyperparameters and functions can be greatly useful in building a successful model.
Yeah, and then just a few more notes on top of that. I think one thing we could spend more time on is fine tuning each individual model for cancer types. Since that model was already more higher performing, if we were able to boost accuracy of some of the lower performing models, then we could boost the overall accuracy, since we know we performed well in some of those. So introducing some PCA or other techniques on those models could possibly improve performance in the future. So yeah, thank you so much, and thank you for listening.